All right, grab your new notes packets. We are going to get started on our 7.6 notes. We are identifying and using trigonometric ratios with right triangles. So on this page, we start with the definition of trigonometry. It is the relationship between side lengths and a reference angle of right triangles. So this trigonometry works with right triangles. We often refer to it as right triangle trigonometry. The general concept here works because of similar triangles. So that's why we learn it at the same time as similar triangles. So let's consider two triangles that are both right triangles, and they both contain a 20-degree reference angle. The right angle is never the reference angle, so it is not the right angle when we say reference angle. The right angle is always separate. We call the side across from the right angle the hypotenuse. Only right triangles have hypotenuses. And the other two sides legs. So you should remember that from our special right triangles lessons. In two triangles that have right angles and the same reference angle, a 20-degree angle, we can show that those two triangles are similar by angle-angle similarity theorem, because we know that 90-degree angle and we know the reference angle. So two triangles that are similar, we're going to see those proportionate side length relationship. Remember the proportions of sides of similar triangles. We have a relationship between those ratios. We know that the ratios, regardless of the size, have to be the same. So we're going to create some functions that model all of the possible ratios in right triangles specifically. So we know that there will be equal ratios of side lengths based on the proportions of the sides of similar triangles, which must be, and I want you to cross out congruent and say equal, right? The ratios must be equal when we have similar triangles. So we can use these consistent ratios to find missing sides of triangles or angles. That's how it's going to be useful. Up to now, if you know two sides of a right triangle, you can find the third side with the Pythagorean theorem. Once we have right triangle trigonometry in our toolbox, we'll only need the fact that it's a right triangle, one side, and an angle to find a missing side. We may also use two sides to find a missing angle. So let's start with sides. Trig is dependent on the relationship between the sides and angle in relation to that reference angle. So depending on which angle is the reference angle changes the perspective. The hypotenuse is always across from the right angle. So I like to find that right angle, draw an arrow, and I know that will be the hypotenuse. Now, good news is the hypotenuse is easy. It is not going to switch up on you. The hypotenuse is always the hypotenuse, and we are not going to worry about it switching. Now, usually we use this angle, this Greek letter theta, looks like a 0 with a line through the middle. It's important that line is horizontal. Sometimes mine is a little curved, but it goes from side to side. And its name is theta. And usually we use Greek letters like theta or alpha. This is another alpha or beta to refer to angles. This is just a kind of frequent geometry convention. So our reference angle theta, this is the reference angle, tells us what side is what. So the opposite side is the side of the triangle that does not touch theta, right? Theta is formed by two sides, the hypotenuse and the adjacent side. The opposite side is the one that does not touch. So that is the opposite side. The adjacent side touches that angle but isn't the hypotenuse. So this is the adjacent side. Opposite and adjacent are always legs. The hypotenuse is always across from that right triangle. So the hypotenuse and the adjacent side will form the angle, and the opposite side will live across from it. So the adjacent side is next to the reference angle. And that's what the word adjacent means. It means next to. The opposite side is across from the reference angle. If the reference angle changes, then the opposite and adjacent will switch. If I make the top angle in this triangle my reference angle, suddenly the green side would be the adjacent side and the blue side would be the opposite side. Hypotenuse always stays the same. All right, so let's meet our three trig functions. We have sine, cosine, and tangent. I always read the word. It is no more than 2 syllables. We do not say sin, cosine, tan, or cos. We say sine, cosine, and tangent. Sine of theta. This is like the square root of a number, right? Sine is a function. We're plugging theta inside it. Sometimes we write it with parentheses. Sometimes we don't. It's not required to, but don't be alarmed if you see parentheses. It does not mean multiplication. It is the sine function where we're plugging in the input theta. The sine function is the ratio of the opposite side of a right triangle compared to the hypotenuse of that right triangle. Cosine, abbreviated with COS, cosine of theta, when we plug in the angle, we're going to see the output as the adjacent side over the hypotenuse, the ratio of those two sides. And finally, tangent, which we abbreviate with tan. Tangent of theta is the opposite side divided by the adjacent side. All right, so you're going to need to remember these ratios. You need to know these in your head, memorized. I will not give you a cheat sheet. However, I have a very helpful mnemonic to help you remember. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We use so, ka, toa. And it sounds a little silly, but sounding it out is helpful. So tells you sine. Sine is opposite over hypotenuse. So SOH, sine opposite hypotenuse. Then we think of ka for cosine. Cosine of theta is adjacent over hypotenuse. Cosine, adjacent, hypotenuse. All right. Finally, we have TOA. TOA is for tangent. Tangent of theta is opposite over adjacent. Tangent, opposite, adjacent. All right? So those so, ka, TOA will help you remember sine, cosine, tangent. So let's see a couple examples. And again, every time I start a problem like this, I'm going to write so, ka, TOA. To help me remember sine, opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite, adjacent. So if I want sine of 40 degrees, I'm using this reference triangle. Conveniently, I have all three sides already. It's a Pythagorean triple, 3, 4, 5. Sine of 40 degrees will give me the opposite, because this is so. So sine of 40 degrees will be the opposite over the adjacent. Sorry, that's tangent. Opposite over hypotenuse. So I'm going to label the opposite side from the 40-degree angle, the adjacent side, and the hypotenuse. Sine is opposite over hypotenuse. Cosine will be the adjacent over the hypotenuse. And tangent will be opposite over adjacent. All right, I notice I'm writing degree symbols every time I use an angle in degrees, so keep that in mind. This is sine. When we plug in 40 degrees, we get out the ratio of 3/5. All right, So I'd encourage you to try example 2, pause the video, try it, and see how it goes. Now, here we're asked to find sine, cosine, and tangent of the reference angle W and sine, cosine, and tangent of the reference angle X. So this sine is going to depend on the opposite side from W and the adjacent side from W, whereas sine of X is going to depend with opposite X and adjacent X. All right, the hypotenuse is always the same. It's across from the right angle. Okay, so sine is opposite over hypotenuse, so the opposite of W is 12. The hypotenuse we do not have labeled on the triangle. So right now I don't know it, but I can find it because I know the Pythagorean theorem. Hypotenuse, and I'll call it little y because it's across from big Y. Hypotenuse squared equals 9 squared plus 12 squared. Y equals the square root of 81 plus 144. This is a reasonable time to pull out a calculator. So we'll see the square root of 81 plus 144 is 15. So 12 over 15 is also going to simplify because 12 and 15 are both divisible by 3. That is 4/5. Cosine is the adjacent of W, which is 9, over the hypotenuse. Both of those are divisible by 3, so we'll divide by 3, which is 3/5. Tangent is opposite W over adjacent W. Both of those are divisible by 3. So once again, 9 divided by 3 is 3. We have 4/3. Sine of X will be the opposite X, which is in purple. That is 9 over the hypotenuse 15. Again, that simplifies to 3/5. Cosine of X is the adjacent X, 12 over the hypotenuse 15, which is 4/5. And tangent is the opposite X. Opposite X is 9 over the adjacent X is 12. So that is 3/4. Notice when you change the reference angle, the tangent flips over and sine and cosine switch. All right. So you try the practice and see how it goes. Once again, we have our hypotenuse, the missing side PQ, I'll call it X for now. We can say X squared plus 14 squared equals the hypotenuse 50 squared. So X will be equal to the square root of 50 squared minus 14 squared. 50 squared minus 14 squared is the square root of 2304. So let's square root that. And we get 48. So this side is 48 units long. And we can then say sine of Q. So opposite Q is 14 over the hypotenuse is 50. I'll simplify at the end. The adjacent of Q will be 48 over the hypotenuse 50, and tangent is opposite over adjacent. If we simplify, 14 and 50 are both divisible by 2, 7/25. 48 and 50 are also both divisible by 2. 48 divided by 2 is 24, and 50 divided by 2 is 25, so 24/25. And 14 divided by 48, both of those are divisible by 2. That'll be 7/24. So when we find sine of R and we use R as our reference angle, now the opposite side is 48. This is opposite R, and the adjacent side is 14. So opposite over hypotenuse is 48 over 50. Adjacent over hypotenuse is 14 over 50. And opposite over adjacent is 48 over 14. So 48 50ths is 24 25ths. 14 50ths is 7 25ths. And 48 14ths is 24 7ths. All right. The next page in your packet looks like Ready, Set, Go. This is your homework, so I want you to start on this and look to the daily agenda for any extra practice that I've posted.